Very good afternoon. Uh, in this lecture, we will discuss about the concept map projection concepts and its application in remote sensing and GIS. So let us discuss this few cases first, and based on that, we will proceed further. So where this concept of the coordinate systems and the map projections comes, and why it is needed. So take an example. In a city, you just have to set up one school, and when you are going for setting up one school on a vacant land, you need to have some information about the land, vacant land, and certain criteria or restrictions will be there, like you cannot means construct the school wherever nearby the garbage land it is there, okay, or some dumping yard or maybe the forest land it is there. We have to construct in a school or set up a school in a place where medium density people should be there, so the people can approach easily. And similarly, you can put another things. It should be nearby to the roads. It should not be far away from the basically the city. Maybe from it should be approachable. So in the if you see the whole things, lot of constraints you can put. The finally you will do when the GIS analysis. You need to have all these information. Now, land information will come from the maybe the municipality or the land records, or the population information. Wherever this will be there, this will be coming from your municipality or the city office. Similarly, the road information will be there from the road department. The garbage, please don't worry, my slides are not changing. Whenever I will change, and it will be changing, okay. So the slide, the forest information will be coming from the forest department. So these all information will be coming in the different of layers. Now when you put all these layers in the GIS environment, and all, if all does not have a same coordinate system or the projection system, the analysis whatever you are going to do for the setting of a school in a vacant land may not be correct. So what you need to do, maybe the forest information is coming in one coordinate system or projection system, and the road information it is coming from the another coordinate system or the projection system. So we need to have a at the same platform, then only further we can go for the basically GIS analysis. Okay, so this was the just one example. Now we are using the basically satellite images also, and satellite images, we for further use we have to assign the proper coordinate, exact coordinates to them, or in the projection system or the coordinate system, so that it can be useful or it can be comparable further, okay. And if we talk about the when we can say the comparison, means like you have some old map, maybe forest map or any other thematic map you have. Now you want to compare that particular map with the today's status, okay, today's imagery, satellite imagery. So what will happen? You have a one side satellite images or the today's condition, whatever it is there, with the proper coordinate system, and it is in digital form, okay. But the tomorrow yesterday what happened, the sorry previous map whatever you have, that is basically a paper map. How you will compare? You paper map, you will digitize it, and you will bring into the GIS softwares like QGIS and other softwares. Then you will, and then when you have digitized it, it does not have any coordinate systems or projection system. So what you are going to do, first you will assign the coordinate system and the projection system to the particular map, then only you will compare with the present condition. So you can overlay and you can see the things, okay. So this is another example. If we say Similarly, you are making your map, you are going for survey, you are mapping that thing, mapping, going for mapping, and you just want to compare whatever the map you have created. And if you don't consider the curvature of Earth means like Earth is not like a flat surface, it's like a curvature of Earth. So if you don't consider, and when you create your map and then you want to compare that map with the present map or the existing reference map, it may match or it may not match because you have not considered the curvature of Earth. And at last, I will say one thing. You always have seen, maybe in map, if you see, there may be the word written like WGS 84 or polyconic. These are the basically datums and the projection systems. So in all maps, generally, they are basically mentioning in which coordinate system and the projection system the map is there. In all country almost, there is a one survey department. Like in India, we have a survey of India. So that department is basically responsible for generation of various kind of thematic or political maps. Okay, so we will proceed further with these applications. So we know the basic stats about the Earth. Its surface area is roughly around 1510.1 million square kilometer. Mass is around 5.97237 into 10 to the power 24 kg. Equatorial radius is 6378.137 kilometer, and its polar radius is 6356.752 kilometer. So this is general our concept. General concept. In generally we think like our Earth is an sphere. If it had been a sphere, if you know the sphere, and if it had been a sphere, then both the radius should have been equal. This is equatorial radius, which is around 22 kilometer more as compared to the polar radius. So in sphere, what happens? Both the radius should be there equal, but it is not here. We will discuss this thing. Then flattening coefficient is around 0.003358. It's about the flatness, how much it is there. Age is around 4.5 billion years. And elevation, you know, around from the mean sea level, we see that 8848 meter Mount Everest, it is there. And there are 7 tectonic plates, which are the African, Antarctic, Australian, Eurasia, North American, and Southern American, and the final one, the Pacific. Okay, so this is just the stats about the Earth. Now, if you see from the space, this is a satellite image of this Earth. What you may be able to see, it looks like a sphere because the radius is around 6378 on equatorial and 6356 around it is there on the polar. So when we talk about this much large scale, 6378 thousands of kilometer, then this 22 kilometer is very minor and it may not be visible. So it looks like a sphere, but it is not exactly a sphere. And we, in terms of mathematics, we cannot say it's a complete sphere. Okay, the first thing. The second thing, which we can see from here, it looks like the Earth sphere is basically plane. It's like a regular surface, but it is not like a plane surface. It's a irregular surface. Maybe the mean sea level, wherever we are seeing sea level, it may be looks like a plane, but other side, if you see, there are the valleys are there are the mountains are there, so it is an irregular surface. It is not like a plane surface. Okay, these two things we can see and we can discuss further. So for surveying and mapping, most of the measurements are taken on the Earth surface, and the surface of the Earth is an irregular surface. Directly using these measured values for further computation of distances, area, volume will give wrong results because the irregular surface of the Earth is not mathematical. If we maybe between the two points, you are going to find one distance. Very simple way you understand. So between 2 points, if you find a distance, the distance may be a straight line. It's maybe a 10 meter. But if it is an irregular surface, and if you are measuring like this, it may be the more. But we have to consider only this distance. So that depends which distance you are going to use. So the surface it is of the earth is an irregular surface. Ups and downs are there. So we cannot use this surface. What we have to do? We have to do the modeling of the earth. We have to define one mathematical model on which we can derive our reference points or latitude, longitude, or we can do the computations in more general, we can say. So we are going to derive basically that particular, what we can say, the geometry of the earth. Okay, so we need a one mathematical surface because it is an irregular surface. Now we will define such a surface which can closely represent our earth, which can be replaced. Maybe we can, it's like a closely it will show the basically the earth. We need a mathematical surface which can closely represent our earth, and we need one model of the earth. So all the measurements can then be reduced to that surface for computations. So once the model of the earth is decided, we need to locate the position of the features. Now what will happen? You have derived the one mathematical model of the earth. Now that mathematical model, that mathematical model, maybe the basically what we can say, it's just whatever the geometry I will tell you, the sphere or the ellipsoid, and in that nothing, maybe we have to derive some reference point. Like if I talk about maybe if I talk about like today I am sitting here at 78 degree, maybe the longitude. Okay, so from where we are taking this measurement, we are taking from the Greenwich meridian. So once the mathematical model of the earth is defined, then after that we will define the reference point, or like height from where we are taking. We are taking from the basically from the geoid or mean sea level or ellipsoid. We will discuss in our lecture. So that reference point we need to define, and after that only the position hour will be estimated, or it will be defined. So height of a point, like height from where it is there, distance from where it is there. Okay, so these all the things will be derived. So we need a one coordinate system, reference system, datum for defining the positions. So now, as I told you in my first slide, that the radius of the polar pole or the polar radius, or the equatorial radius, both were not same. There are around 22 kilometer difference. It is there. So our Earth is not perfectly spherical. Now, how to represent basically the shape of the Earth? So the answer is the shape of the earth can be best represented by an ellipsoid. Now the question comes, what is an ellipsoid? Okay, we will discuss this thing. So if you see left side figure, I have just figured it here that the circle, and circle, if you see from center to circumference, that the distance is called the radius. Okay, the point A to point B, it will be a radius, and that radius will remain same throughout the circle. Wherever we will measure, it will be same. That is called the radius. Now double of this radius is called the diameter. Okay, and the equation of this circle is x square plus y square equals to a square. One simple equation. Now double, as I told you, the double of this radius is the diameter. So circle is a basically two-dimensional geometry. Two-dimensional means that two variables will be there, like x and y. Okay, now what is an sphere? Now what you do, you just take about the diameter, you take, okay, diameter of the circle, and just rotate it about its diameter. Rotate it about the diameter. Take the circle and rotate it about the vertical diameter. It will be clear, the vertical diameter. Now you imagine one three-dimensional geometry will be creating. What is that? That is an sphere. It will be looking like an sphere. Okay. Now, what you do, but our Earth is not clearly representing the basically the what we can say that sphere. It's not perfectly sphere. So what we have to do, those are not from mathematics. Just I will explain like a very simple way. You take the circle and just press from top and bottom. Okay, just press from top and bottom. So the you may see the right side figure, whatever it is there. So right side figure, it looks like this one. Now, instead of vertical diameter, because that is reduced, the distance is reduced, it has become the, it is reduced, and the horizontal diameter, what was there in case of circle, it is now expanded. It is more now. Okay. So what the reduced one, the vertical one, we call it as a minor axis, and the expanded, whatever the horizontal diameter, we call it as major axis. Okay. Now what you have to do, the half of the minor axis is called the semi-minor axis, and half of the major axis is called the semi-major axis. So instead of radius, in case of circle, we have a here semi-major axis and the semi-minor axis. Okay. Now, and that is called the semi-minor axis, we call it as a here, representing by A, and semi-major axis we are representing semi-major axis we can represent it by A, and semi-minor axis we can represent it by B. Okay, and this is an equation of this ellipse: x square upon a square plus y square upon b square equals to 1. Now, first case, if A equals to B, if A equals to B means if minor axis is equal to the major axis, so A equals to B. So what will happen? X square plus y square, and A square will go this way. So x square plus y square equals to A square. So it will become a circle. If A equals to B, then this will be a circle. Okay. Now, so you have pressed, and what you got this minor axis. Okay. Now, earlier case you rotated about the diameter. This time you rotate it about its minor axis, the minor axis. Okay, minor axis. Okay. Now, when you rotate it about its minor axis, you may see that some flatness from top and bottom, and you may see that basically a three-dimensional geometry, whatever it is coming, it is an ellipsoid. Okay, so just a minor difference from the sphere to this ellipsoid, it will be there. Both places you are rotating about its vertical axis, here minor axis, here the diameter. Okay. Now, only thing is that how much you have to basically, maybe that's I was telling now. If you are pressing more flatness will come. It will be like ellipse will be more flattened. Ellipse will be there. If you are pressing less, and less flattened ellipse will be there. In terms of eccentricity, we can measure it. Okay. And so an ellipsoid is the mathematical surface which can be generated by rotating an ellipse about its minor axis. Such ellipsoid is called an oblate ellipsoid. So we have to rotate about its minor axis, and that ellipsoid is called an oblate ellipsoid. Okay. So, and when ellipsoid it is there, we have to represent it by certain parameters. Like in case of a sphere or circle was there, we have a radius, we have a concept of diameter, we have a concept of circumference. Like that, similarly, we have a some parameters in which we represent an ellipsoid. Okay. So one is a basically semi-major axis, that is a A, and another semi-minor axis, the half of the distance, half of the vertical distance, that is a B. Eccentricity, E square equals to A square minus B square upon A square. This is a new concept. New terminology has come now. So I will explain this one. Eccentricity shows just how much it is away from your circular position. Okay, eccentricity shows how much it is away from your circular position. So suppose E equals to 0.0001. That means it is more close to the circle, more close to the circle or the ellipsoid, sphere. Okay, E should be, ellipse is very much close to the circle. Now, if E is suppose it's a big number, like suppose 0.8 or 0.8, so it's a highly elliptical, we can say. Okay, so that way we represent our eccentricity. Now, if you know in our Earth case, A is almost equal to the B, but A is not equal to B because A is how much? 6378.137. B is how much? 6356 around. So A square minus B square, if you take the difference and divide it by A square, so E will be very much less. So it is not highly elliptical, it is less elliptical, but E is, in case of circle, what will be there? If A is equal to B, A equals to B, that means circle case. So A will be B, so it will be a 0. So in circle case, eccentricity will be 0. But if it is some number it is coming, A is not equal to B, that means some eccentricity is there. And in that case, ellipsoid will be there. Okay. And similarly, we have another concept of flattening coefficient F equals to A minus B divided by A. It is just a ratio between this A minus B and A. It shows the flattening coefficients. A reference ellipsoid has its center a close approximation of center of mass of the Earth and minor axis is parallel to the axis of rotation of the Earth. Yes, please. Someone. Okay, so a reference ellipsoid had center close approximation of center of mass. So ellipsoid, whatever it is there, it's a close approximation of center of the Earth. And then minor axis, which was there, about which we were rotating the ellipse. Okay, so it is close to the, maybe its axis is the parallel to the axis of rotation of the Earth. Okay, latitude, longitude, and ellipsoidal heights are defined on reference ellipsoid. So now you understand, you are seeing the globe, it's an ellipsoid. Latitude, longitudes are defined on this ellipsoid. Okay. Now there is another term, ellipsoidal heights. So this latitude, longitude are for the basically horizontal measurement where you are there. Okay, but ellipsoidal heights, if you want to go to the vertical, you want to measure the vertical, how much it is there. So if vertical, for that reference point you need, so we can take it from either from this particular ellipsoid, we can take from the mean sea level, or we can take from the geoid. Okay, so for vertical there are the many options are there. We will discuss all these things. Okay. So it looks like, see, this is a blue line. Blue line, it's an ellipsoid. It's a more close to the Earth's surface. As I was telling, Earth's surface is an irregular surface. You may see somewhere mountains will be there, somewhere valleys will be there, and somewhere it's almost looks like an sea level. Okay, our that ellipsoid, the mathematical model, whatever we have defined, it closely fit into this Earth surface. Okay, so this is an Earth surface and this is an ellipsoid, and you know the B is the semi-minor axis and A is the semi-major axis. Okay. Now, now the terms comes the types of the reference ellipsoid. Okay, so in that case, we have two types of ellipsoids. One, best fit ellipsoid, another one, geocentric ellipsoid. Okay, so we will discuss this thing. First thing we came to know now, some mathematical model which is closely representing our Earth, that is an ellipsoid. Okay, now we have two terms here, best fit ellipsoid and the geocentric ellipsoid. If you see in today's time, generally we are using this WGS84 commonly. So this is an example of geocentric ellipsoid. Best fit ellipsoid, what happened in earlier times, like today's technology, we have a GPS, global positioning system. We have a VLVI technique, very large boundary interface. That VLVI technique, that's another measurement techniques we can understand. Uh, Lunar laser ranging, or different type of techniques we have in today's time, by which if we measure, then we can have a better or more precise ellipsoid. Okay, we can determine. But the earlier time, when we have a maybe century back, if we go, then we did not have a that much kind of technology. So what we did, we have collected the local information. Okay, and based on that local information, we have developed or derived the ellipsoid. Okay, so in India also, like local information we have used, and we derived our ellipsoid. So if that type of ellipsoid, maybe when using the local information, if we are deriving that particular ellipsoid, may be more suitable for that particular region, and it may not be suitable, may not be, I'm not telling the exactly, but the may not be suitable for the other side of the region, for the other region, because while deriving this type of ellipsoid, local informations are used. So this ellipsoid is based on the measurement within a region, so it best fit that region only. The center of such reference ellipsoid may not coincide with the center of gravity of the Earth. An example of such ellipsoid is Everest ellipsoid, which was used in India. So in earlier, till now we were using this Everest ellipsoid also. Uh, I will discuss later about this ellipsoids, which country and whatever, as you are telling, the questions is coming. So I will discuss this thing in last I will discuss the, you take your questions. Which was used in India. So geocentric ellipsoid, as the name suggests, that the center of geocentric ellipsoid coincide with the center of the Earth. This type of ellipsoid can be used worldwide. As an example of this type of ellipsoids are GRS 80 and the WGS 84. So when if you see, this is the basically figure. The blue one, if you see, it's a basically center of geocentric ellipsoid. The red one, it is basically, you see, it is geocentric, means the center will coincide with the center of the Earth, as you can understand. And it is, the green one is the Earth surface. The red one, it is a basically matching with the Earth surface. And if you see the blue one, it is a best fit ellipsoid. Its center may be somewhere different from the center of the ellipsoid, but if you see, it may be suitable for this right side region, the blue one, but it may not be suitable for this red side region. Red one, the other side, if you see the left side, it may not be suitable for that particular region. Okay, but it may be suitable for the right side region. Why? Because we have used the local information, which is right side information, to derive such kind of ellipsoid. Okay, so India also developed this, as we were discussing the best fit ellipsoid example. The Indian geodetic datum used till few years back was realized during 19th century. It was a result of great trigonometric survey carried out from 1802 to 1839. The conventional triangulation method was used. It was the best available technique at that time. The series of connected triangles from southernmost point of India up to the Himalayan foothills was used to compute the arc distance, what was named the Great Arc. The Great Arc measurements were used to determine the geometrical parameters, semi-major axis and the semi-minor axis, to define the reference ellipsoid, which was named after Sir George Everest as Everest ellipsoid. This is locally fit ellipsoid with the following parameters. So what the India people did at that time, if you see the next slide first, then if you see that it's a series of connected triangles, they mapped from our southernmost point of India, from Kanyakumari to the northern most point near to the Everest Himalaya. Like this, they have basically done the Great Trigonometry survey, and you see the left to east to west and north to south. So many arcs are there. So what I told to you in that, basically it was a series of connected triangles. Means if I am standing here and if I take the two rows here to chain and like that, and then we can make it one triangle, equilateral triangle kind of things, and then we can go further from these points. So like that they have mapped. Because if you don't take triangle means angles in between, then you may deviate from the directions. So for the direction purpose it's required. So that was the basically best available techniques at that time. And if you basically that name is the Great Trigonometric Survey, the name was there. And it the Sir George Everest was there, and he, based on that only, the name, the ellipsoid whatever he has derived, so its name is the Everest ellipsoid. So till now, you know, if we are deriving a ellipsoid means we are deriving a certain parameters. What is our semi-major axis? What is our B? That what is our eccentricity? All these things we are deriving. Deriving a ellipsoid means all these things you have to tell. Okay, so they have what they have done. They have just only measured the one arc from. If you see the ellipsoid from the one part only, and from India southernmost to the northern Himalayan region, they have measured, but they did not have any information of the around the globe. They have used only the local information, and based on that, they have developed the ellipsoid. Hmm? Based on that, they have told this will be the A, this will be the B. So that much accuracy was there in the mathematics. And if you see, and if we compare this Everest ellipsoid with the presently available GRS 80 ellipsoid, so if you see in the semi-major axis, GRS 80 is the basically today's geocentric ellipsoid, which is developed using the latest available technology. And if we compare with the 6377.301 in the semi-major axis A, which was developed in Everest, and in GRS 80 it is the 6378.137. So if you see, it's around 800 meter only difference it is there. So if that time whatever the developed that datum was developed, or this ellipsoid was developed in India, and it was maybe generally if local information we are using, that some may not be suitable for the other reason, but it is how much it is closely there. It's a more close to the geocentric one. Only 800 meter difference it is there in the Everest and the GRS 80, and which was developed in the 1802, and this is developed in the 1839. Oh, sorry, nowadays 1802 to the 1839. That econometrical survey was there, and that time it was developed the Everest, and till this year now today we have a GRS 80 with this. Okay, so that much accuracy was there. That much precisely they have estimated this ellipsoid. Similarly, we have a, so this was all about the ellipsoid. Now in this ellipsoid, what we do, we have a maybe we will derive the so many parameters like axis of rotation from where it will pass, x-axis from where it will pass. Till now only you have a ellipsoid. It's just a mathematical thing. In that, so many things you have to put to derive the to make it means more appropriate representation of the Earth, like axis of rotation, like x-axis from where the Greenwich meridian will pass. Okay, where will be the North Pole, where will be the South Pole, kind of things. All the things you will derive, and then it will be called as a datum. Okay, so now you have our ellipsoid, that mathematical model of the Earth, and that is an ellipsoid, and on this you can derive latitude and the longitude. So one information you can derive from this latitude and longitude. So now other information, whatever it is there, height information, you can take it from either from this reference point ellipsoid, or you can take it from the geoid. Okay, there is another term. Geoid is an equipotential surface level, surface of the gravity field which best fit the mean sea level. So mean sea level, you know the mean sea level, how we are deriving, because we mean sea level in all countries generally we are estimating. So we are mean sea level means we are considering here the high tides, low tides, atmospheric effects, gravity effects, and the other wind effects. All the information we will collect, and then a long-term analysis we will do, and then after that only we will say this is our mean sea level. And if we say in out of that, only if you take the mostly part of the gravity, only gravity related things if you take, so it will be only the field will be called as a geoid. So geoid and the mean sea level both are close, both are very much close. The only thing here we are taking in some extra effects we are taking. So it is an basically equipotential surface where the geopotential, or if we talk about this gravity based surface, in that at all point the geopotential will remain same. Geopotential is, we can say, like gravitational potential energy plus centrifugal potential energy kind of things. So more general I will tell that it's basically related to the geoid, because in GIS we are doing all the analysis related to the gravity field. So we are just we need to have a height from either from the mean sea level or from this geoid kind of things. Ellipsoidal heights generally we are not considering in our GIS analysis. Okay, it is nearly ellipsoidal but a complex surface. It is not a mathematical surface. It may be defined as surface coinciding with mean sea level in the oceans and the continuing under the land at the level to which the sea would reach if allowed to flow through frictionless channels. So how we are representing a point, suppose it's a blue, here one point it is there. And so horizontal generally we are considering as an ellipsoid, and vertically we are taking as a reference from the geoid or mean sea level. Okay, and if you see the small h is the basically the vertical height from this maybe the point, the height and the distance or height we can say from this ellipsoid. Okay, straight line. Then h is the basically geoid, geoidal height if you see. Okay, and if we take the difference between h, small h minus h, it is called the height difference, is called the basically geoidal undulations. Okay, so we can derive this geoidal undulations. Now this maybe somewhere this will be more, somewhere blue line will go down, somewhere this red line will go automatically, is like it's a mathematical surface. So as per the equation it will go, it's based on the gravity field, so be somewhere up somewhere down kind of things will be there. So based on that we can derive the difference between the orthometric height and the ellipsoidal height. Now with reference to ellipsoid, how we representing a one point? So suppose point P it is there, point P. Now if you see the vertical distance, basically if you see the normal distance, if you draw from this point P to the normal to the surface of this ellipsoid. So you draw one normal or perpendicular to the surface of this ellipsoid. It will pass through this ellipsoid and somewhere it will meets to the axis of rotation. With the purple color you are seeing, it's a equatorial plane basically. The equatorial will pass from here. Now if you see the perpendicular distance, maybe from the surface to the point P, this is called the basically ellipsoidal height. Just generally we were discussing Havarna at a small h. So this is a basically ellipsoidal height. So this is an ellipsoidal, h is the ellipsoidal height. Now if you see, it will when you are drawing a perpendicular, then somewhere it will cut the surface of the earth and surface of the earth, and from where one meridian will pass. Okay, that is called the basically observer's meridian. Okay, observer's meridian. And if you have already some reference point, that is the red one. So if you take an angle bit from this Greenwich meridian to the observer's meridian, that is called the basically longitude lambda. Okay, and similarly wherever it is cutting here surface, and from the equatorial plane to this blue line, the angle if we measure, that is called the basically phi, and that is the basically another, that's called the latitude. So you have a longitude, you have a latitude. These are the basically for the horizontal position. And for vertical position, you have a perpendicular distance from the point P. It is nothing but the ellipsoidal height. So that way also we are deriving a latitude, longitude, and the ellipsoidal height. And latitude, longitude are for the basically horizontal position. Height you can take it as from the either from the geoid or the mean sea level. So latitude, the angle subtended at equatorial plane by the ellipsoidal normal through the observer's point. Longitude is the angle between the observer's meridian plane and Greenwich meridian plane. And we have an ellipsoidal height, the height above the surface of ellipsoid measured along the ellipsoidal normal. So till now we were what we discussed. We have discussed about one three-dimensional geometry, which basically Earth is by which using which we can closely represent our Earth, and we have derived the latitude, longitude, and a point height, the height. So we can say where we are standing here. We are at 78-degree longitude. Longitude is from Greenwich meridian. We are at 30-degree latitude. Latitude from where? The angle between the equatorial plane and the observer's meridian, wherever I am sitting. So observer's meridian, wherever it is normal, the whatever it is there. So that is the latitude. And height. Height may be a 650 from the mean sea level if we say, or from the ellipsoidal height if we say, maybe something else will be there. Okay, so that way we can represent our position on the three-dimensional geometry. Now, still now we were discussing about the three-dimensional geometry, means either we were discussing about longitude, latitude, and the altitude and height, whatever it is there, or in terms of x, y, z. These latitude, longitude, and height, whatever you are seeing here, actually first we derive the axis, the coordinate axis, the x-axis which passes through the Greenwich meridian, suppose, and y-axis which is perpendicular to the x-axis and it is passing through the equatorial plane, and then z-axis which will be perpendicular both the axis and the axis of rotation of the Earth. That way generally we derive, and either we have an equation in the form of x, y, z, or it will be in the latitude, longitude, and the height. We can derive from one to another. We can convert x, y, z to the latitude, longitude, and altitude, and the other way also we can derive. So this is the basic. When three parameters involved, it's a three-dimensional geometry we were discussing. Now, for the various analysis, or carrying like you are carrying different thematic maps, we have to convert this three-dimensional map onto a two-dimensional, three-dimensional geometry onto a two-dimensional map. So the transformation or the conversion from three-dimensional to the two-dimensional geometry is called the map projection. Okay, here only the two terms will be there. If you see here, one left side, latitude, longitude, height, or x, y, z are written. If you see the right, x and y are written. That means here the latitude, longitude information will be there. So this is the basically three-dimensional to the two-dimensional conversion, transformation. So map projection is a transformation of three-dimensional space onto a two-dimensional map, a systematic arrangement of intersecting lines on a plane that represent and have a one-to-one correspondence to the meridians and the parallels on the datum surface. So there will be a one-to-one mapping of the line, whatever the latitude and longitude are there. There will be it will be there on this two-dimensional map as well. Now, this three-dimensional geometry you can convert or transform to the two-dimensional map on the different ways using different geometries. Like example, if you are seeing the cone here, so you just take a one cone and just put a one globe on side inside that cone, and then you what you do, just project onto the wall of this cone, and then you unwrap it. So when you unwrap it, you will be end up with a one two-dimensional map. And similarly, you can use this flat sheet also directly and put onto the wall or onto this sphere or geometry, the ellipsoid, and then you project onto the wall of this two-dimensional map. So already it is there, the two-dimensional sheet it is there, so you no need to unfold it. So it will be a two-dimensional map. Similarly, you can use the another geometry, which is nothing but the basically cylinder. In cylinder, you can put one globe, and then you project onto the wall of this basically cylinder, and then you unwrap it. So you will be end up with the one two-dimensional map. So there are the various geometries by which you can also have some different kind of two-dimensional map. We will different certain map projections. Now, types of map projections. So different type of map projection can exist based on the, like, one is a equal area. Equal area means the maintain equal relative sizes used for the map that show distribution, or another phenomena where showing area accurately is important. It's like an example, Lambert azimuthal equal area, the Albert equal area conic. Okay, so what happens here? We just need to maintain the area between, either it will be in proportion or the same area whatever we want from this type three-dimensional to a two-dimensional, then we are converting it. So such type of map projection, when we are maintaining the area constraint, that is a basically type equal area projections will be there. Then we have another kind of projection where it's called is conformal. Yeah, here basically we just want to preserve the basically shapes, what we can say, the small or over small areas. So it maintains the angular relationships and the accurate shapes over small areas. Is basically used for the angular relationships are important, such as for the navigation and the meteorological charts. So Mercator kind example is are the Mercator, Lambert conformal conic, LCC are the examples. So here what we will do, we will just want to preserve the basically shapes. In first case, we want to preserve the area. Second case, we wanted to preserve the angular relationships or the shapes. Similarly, we have an equidistant map. Maintain accurate distance from center of projection or along given lines. So from center of projection to the particular point, if you want to maintain a distance should be remain same when we are transforming this. So that type of projections will be there, equidistant projections. Okay, basically used for the radio and seismic mapping and for the navigations. Equidistant, conic, and equirectangular are the examples of such type of projections. Now we have a final another one, that is the azimuthal or the zenithal. It maintains the accurate directions and therefore angular relationship from a given central point. So we have a one central point, and with respect to that, we want to measure the accurate directions and angular relationship should maintain. So that's basically azimuthal or zenithal type of projections used for basically aeronautical charts and the other maps where directional relations are important. Examples, mnemonic projections. I will show you the some of the maybe projections figures so you will understand better. Map projections can be classified based on their method of construction. There are many surfaces which are not plane but which can be created by rolling a plane surface. You understand, just now we discussed about like a cone and a cylinder. They are not plane surface but which can be created by rolling a plane surface. You project onto the wall of this cylinder or cone, and then you unwrap it. It will be converted onto a two-dimensional map. Such type of surfaces are called developing surfaces. Cylinder and the cone are the such surfaces, and the map projection can be created by placing such surface on a global, projecting the features from globe to the surface and then unwrapping the surface to make a plane map. So excuse me. Based on the extensive property, we can derive, like we can use the plane, cone, and cylinder nature wise. Tangent, secant, and polysurficial means one by one we can see the figures. So if you see here, we can use the cylinder, we can use the cone, and we can use the what we can say plane map or plane two-dimensional sheet. Now, if we see the example here, the coincidence by if we do the classification, the tangent, secant, and the polysurficial means tangent. Tangent in the case, I just show you the figure. If you are putting a two-dimensional sheet like this onto this surface, it is just touching. It is not crossing the globe anywhere. Whether we put like this, we like this, and like this. But in all case, it is just touching the surface. So this is called a tangent case. Now, if you see the cylinder case here, the globe is inside, okay, and it is just touching the surface, the equatorial region. Okay, so this is a basically tangent case. This is a tangent case. So if you see this is a tangent. Next is the basically secant case. Secant case is the basically, if you see if the radius of this what we can say cylinder is less as compared to this globe radius, then it will cut here. Okay, it will cut and it will pass from the other side. It will come from the other side. Okay, what exactly meaning I will explain. So, but this is the second case. So second case, it is just the radius is less, but tangent means it is just a touching, and polysuperficial means in that where more than one geometry is basically we are using. Okay, I will show you. And then we have a position wise, if we see the transverse or normal, transverse, and oblique case. So if you put the cylinder in this way, okay, vertical way, okay, so then it is a normal case. And if it is you are putting a cylinder in a horizontal way like this, then it is a transverse case. And at any angle, if when you are putting apart from normal and transverse, then it is an oblique case. So as per our requirement, we can use the projections. I will come to that point. So this is a basically transverse case, but it is a tangent case. If you see this figure, the tangent case and transverse case, but here it is a tangent case, but the normal case. Here the secant case and the normal case. And here if we move this like this, make it in the transverse position, then it will be a secant case and the transverse one. So different type of map projections can be created using this. Okay, so this was there, and then oblique means at any angle if we put, then it will be an oblique. So if we take an example of this azimuthal projection, you see the two-dimensional map it is there, and we put like this, and then we project onto the two-dimensional map, and then we can get a two-dimensional sheet. Okay, sorry, two-dimensional sheet we are projecting, and we are getting a two-dimensional map. And then we can put it on the equatorial region as well. We can put it on at oblique case as well. Like that we can put. So this was the cylindrical case, as I was telling to you. It's a cylinder was there, and it just maybe touching the basically wall of this cylinder. And if you see, when it is a tangent case, so only one line or equatorial or any other meridian or what we can say meridian, latitude, longitude, parallels, and this will be touching at one place. Now wherever it is touching, when you after projection, when you unwrap it, after projection onto this wall of this cylinder or any other cone, when you unwrap it, then there will not be any distortion along this line. Okay, there will not be a distortion along this line. So this is called a standard parallel here. This is an standard parallel. When you are moving away from this line, then the distortion will increase. Whether you are moving up onto the North Pole side, whether you are coming down to the South Pole side, so the distortion will increase. Now, second case, what will happen, since the radius was less, so it will cut at two places, and you see, so there will not be there are the two standard parallels are there, two blue lines, that bold one you can see, there are the two standard line. So there will not be any distortion along these lines, but when we are moving away, so distortion will be increasing. But in first case, if you see, the distortion will be more at the polar region, but here will be, in this case, the less distortion will be there in the second case. Okay, so this was an example of the normal, maybe the cylinder. Now you can put the cylinder, and at 90 degree you can turn, and then it will be a transverse case. Okay, and in the transverse case, you may have a similar like a tangent and a secant, and you have at any angle, if you put this globe inside that, then it will be an oblique case, and oblique also tangent can be there, or the secant can be there. But the line wherever it is touching, it will be a one standard parallel, or two will be there, or when two will be there, the distortion will be maybe increasing, but it's less, it is coming in this case. And when it is equatorial, only one line it is touching, so there is no distortion, but when we are moving away, the distortion will be increasing. In the conic projection, similarly, like what we can say, the cylinder and the cone. Okay, so cone, if you see, if it is a touching case, only one point line it is touching, so there is a basically one standard parallel will be there, and when it is the second case, there will be a two standard parallels will be there. Okay, so many properties can be measured on the Earth's surface. Some of these properties are area, shape, directions, distance. Map projections can be constructed to preserve one or some of these properties, though not all of them simultaneously. Now, you can derive different kind of map projections. Various map projections can be existing. You can tilt it, you can put in oblique, like this, different kind of map projections can be existing. Okay, now these map projections preserve at least one property, or maybe two property, but not all properties. Like you want to preserve the area, you want to preserve the shape, you want to preserve the directions, the distance, whatever we discussed. You want to preserve all. It's not possible to preserve all these things. You want your area should be preserved, or this what we can say, the distance or the directions or the figures, everything should be there, should be preserved. It's not maybe say almost not possible, but maybe all different map projections, what they do, they try to preserve the at least one property or two property, depending on the projections type whatever we are using. So each projection preserve or compromises or approximate basic metric properties in a different ways. The degree and the kind of distortion vary with the projection used. Some projections are suited for mapping large areas that are mainly north-south in extent, other for large areas that are mainly east-west extent. Okay, so as I told you, some of the basically map projections are preserving one property, some are preserving different properties. So there are the various map projections exist now. Okay, the first thing you remember, that was the datum or the ellipsoid. That also we have a different. With how we have a different one, we have a best ellipsoid, another one we have a geocentric ellipsoid. In geocentric, we have a GRS 80, we have a WGS 84, we have a X, Y, Z, so many are there. Okay, like X, similarly, we have a best fit ellipsoid. We have developed in India, that was a Everest ellipsoid. Similarly, we in your country, maybe some ellipsoid was developed. Maybe the third country, the other ellipsoid will be there. So there are so many ellipsoid. Here also there are the geocentric also different ellipsoid. Best fit also so many ellipsoid are there. Okay, first thing. Now In this ellipsoid also two-dimensional conversion they have done. Okay, so two-dimensional conversion when they have done means the different projection existing. Like one, suppose an example X type of ellipsoid, or you take an example WGS 84 ellipsoid. From WGS 84 we have a type of A projection, we have a type B projection, we have a C type projection, D type projection. Maybe one in A type projection we have used the cone. Another B type projection we have used cylinder. C type of projection, what we did, cylinder we have taken, but we have taken the transverse cylinder. D type of projection, what we have taken, suppose we have taken the cylinder, but on oblique case we have taken. So different, what I mean to say, this is just one using one ellipsoid. Similarly, using other ellipsoid also, there are the various map projections are available. Now we have a different ellipsoid, we have the various map projections are available. In this various map projections, they will try to preserve some of the properties. Okay. Now the question comes, as per our convenience, we can use this map projections. As per our requirement, convenience in the sense the requirement. Some map projections are basically used for the north-south extent, maybe good for the areas which are having a more north-south extent. And some map projections will be used which are having a east-west expense. Maybe the country which are having a east-west expense, like country name, if you know, it will be there, China will be there, Russia will be there, and USA will be there. So they are having a more east-west expense. But the countries which are having a north, the projections, whatever we are using here, we may not use for this northwest expense. So we will use here the different map projections. Okay. Similarly, you are doing certain analysis for your field also, the maybe the agricultural field, you want to somewhere the water body person or maybe the agricultural person. So objectives are different, themes are different. They may be using the different kind of projections. So first thing. The second thing is that the ellipse projections and the ellipsoid. Ellipsoid in today's time, we are generally basically using this WGS 84, which is globally accepted. And when we are giving any map or figures or pictures to the another country, suppose images if I am sending, and if it is in WGS 84, it is it is easy to accept it. Otherwise, what we have to do, if we are giving in, suppose I am giving in Everest datum, and you have a certain images in WGS 84. So what you have to do? You have to convert this Everest ellipsoid to the WGS 84. Okay. So WGS, that because in beginning itself I told that's we need some common platform. Then only we can do some comparison. And so for that, either we can transform that image into the Everest ellipsoid or Everest to the WGS 84. But we should know the relation. We should know the relation between the Everest ellipsoid and the WGS 84. Means we should know the equations which can transform this WGS 84 to the Everest or Everest to the WGS 84, or X to the Y or Y to the X. So we should know the relations or set of equations by which we can convert from one to the another one. Okay, so that way we generally, as per our requirement or as per our applications, we generally select our datum or the map projects. Okay, and you know the property of the projection, this equidistance, conformal, where the distance remains same, and the conformal and the shape will be preserved, and the equal area. And generation wise, we are using the mathematics also, we are using the geometry also. So it's a geometry, semi-geometry, and the mathematical. So equations are obviously required. So some examples if I take here, if you see here the globe inside that cylinder, and after that we have projected onto the wall of this cylinder, and then we unwrapped it. After unwrapping, you may be able to see the two-dimensional map, which is basically projected map. So cylindrical map projections are made by projecting from the globe onto the surface of an enclosing cylinder, and then unwrapping the cylinder to make a flat surface. So Mercator and the transverse Mercator, just an example of these types. So in Mercator type of projections, what we are doing, it's a cylindrical. You can see in the black cylinder, one globe you can see, and we have a here conformal, means we want to preserve the shapes, not worried much area in about the area. And after projection and then unwrapping, we will be end up with this two-dimensional sheet. Now, what you can see in this two-dimensional sheet here, meridians are equally spaced straight lines. Meridians in the sense, basically what we call longitude. Okay. So these are the equally spaced straight lines. You can see straight lines are there. Okay. Then parallels are unequally spaced straight lines. Parallels means the latitude. If you see the distance is increasing from equator to when we are moving towards the North Pole or South Pole, so it is increasing. And great distortion of area in the polar region. Sorry, the first line is the scale is true along the equator. So as I told you, when it is a tangent case, the line will be touching, and then scale is true along the equator. So there will not be any distortion along this line. Okay, and great distortion of area in the polar region. When we are moving away, the polar region, if you see, this is the area, if you are able to see, this is a Greenland, and you can see how much distortion it is there, because Greenland area is seeing looks like so much big than Indian area, if you see, because in India is very near to this equator, so there will not be any distortion. But this Greenland looks like this half of the Africa or more than that it is there. So it is just because of distortion, great distortion of area in the polar region. So similarly, we have a conic projection. For a conic projection, the projection surface is cone shaped. Instead of cylinder, you can take cone. Locations are projected onto the surface of the cone, which is then unwrapped and laid flat. Okay. Here, there was a Mercator. Here, in case of that, LCC is the famous, maybe well-known projection. Conical, it's conical, and conformal means shape will be preserved. Parallels are concentric arcs. Meridian are straight lines. Cutting parallels at right angles. Scale is true along two standard parallels, and normally or just one. In case of secant, it will be two, or it will be a tangent, it will be a one. It projects a great circle as a straight line and used for maps of countries and regions with predominant east-west expanse. Okay, used for plane coordinate system in USA. So USA already have I told you that it is in more in the east-west expanses, so they will be using. You may be seeing here that one tangent it is there, and two standard parallels are there. Here in case of one standard parallel will be there. It's a tangent and the secant case. This is the LCC projections. So you can see here the meridians are straight lines, cutting parallels at right angles, and these are the parallels are the concentric arcs are there. So these are this kind of map projections we will be getting. So this map projection is more suitable for the basically countries east-west expanses. Polyconic projection. In this projection, all parallels are projected without any distortion. Scale is exact along each parallel and central meridian. Parallels are the arc of circles but are not concentric. It is neither conformal or nor equal area. Central meridian and equator are straight lines. All other meridians are curves. I show you the picture. Basically, in this polysuperficial, maybe in this polyconic projection, what we do, we have a different what we can say, the cone of different sizes, and whenever it is touching at wherever it is touching at the globe, we are taking just one strip. If you see the orange cone, from the orange cone, orange strip, green cone, green strip, and the blue cone, blue strip we have taken. And I know, and you also know that so when it is touching, and there will not be any distortion along this line. So that way distortion will not be there, and we will take a small strips and we will put it together. Okay, so in this such type of map, we will try to minimize the distortion. We will using the different sizes cone or different geometries. This type of cone try to preserve all properties, but not all of them exactly. Okay. Number of cones increases to infinity, each strip infinitely narrow. The result is continuous polygonic projection. So when this strip will be the small, it will be very closer. The green one will be closer to this red one. So like that, continuously, what we can say, continuous map, we can get it. We have an example of azimuthal projection. For an azimuthal or planar projection, locations are projected forwarded onto a flat plane. The normal aspects for this projection is north or the south pole. Generally for the north-south pole we are using. So it's a defined above 84 degrees north latitude and below 80 degrees south. And it's a conformal. Meridians are straight lines, parallels are circle, used for basically conformal mapping of polar region. So this is like azimuthal projection. Mainly basically used for the this north and the south. Then we have in one more concept of the universal transverse marketer UTM grids. What we are doing, whole map we are dividing into the 6 degree longitude and 8 degree this latitude. So like that we are defining in the zone wise what we're deriving. Okay, like in Dehradun we are here in UTM 44 zone. Okay, so when for the area is very small and we want to do like a very maybe small area exercises, we no need to go for the like a projection kind where distortion will be there. So this is generally used for the where we try to minimize the distortion, or we can keep the distortion within a one zone itself. We no need to go further. Like if we are doing certain analysis which is beyond this UTM 44, I will use the UTM 45 zones. Okay, there are the certain parameters are there, we are deriving the central meridian 500 kilometer, and then like that different parameters are there to derive this map projections. Okay, so then choosing a choice of a map projection is made to give the most accurate possible representation of the geographic information, given that some distortion is inevitable. The choice depends on the location, shape, size, and the theme or the purpose of the map. As I told you, there are the various kind of datums are there. From that, there are the various map projections are available, and we have to select the map projection as per our location, as shape or the requirement or the purpose of the map. See, LCC map I have used for the USA mapping, and this marketer we are using for this basically transverse marketer we are using with this for this UK map. I cannot use this map, this type of projection for this what we can say USA mapping or LCC we cannot use, because LCC if I use for the UK it will be spreaded one. So it will distort the basically objective shape. So different of map projects, different type of map projection exists, and we use this map projection as per our requirement or the purpose. And when we are deriving the map, lastly we are giving a one map, then we are giving a along with the map, projected map, we need to define the certain parameters as well. You always see it's written on the map of your countries, or like in which datum, which projection system it will be there. So similarly, to define the coordinate system completely, it is not sufficiently simply to name the kind of projection used. It is also necessary to specify the projection parameters, like where is the central meridian, where is the standard parallel, all these things we have to, which datum, which projections we are in, everything we have to define. It is important to know the projection and the projection parameter used in map imageries. Sometimes it is required to superimpose one map or image on another map. If map and imagery have different projection parameters, the detail will not match, and if they are superimposed. As I told you in beginning, if you want to compare two maps, they should be in the same projection system or the coordinate system. The set of parameters required depends on the kind of projections. So what are the parameters we are giving? The central meridian of the projection for cylindrical, where it touches the ellipsoid surface, standard parallel for conic projections, the false easting, false northing, one more concept it is there, the units in which they are the reference system or the ellipsoid. So we need to project the geospatial data for area analysis for different type of GIS analysis we are doing, and in that we are using the various kind of geospatial data. Make it possible to use data from different sources. The data will come from the different sources. As I beginning itself, I gave an example like one road department data will come from municipality. The population information will come, density area will come. So different data will come from the different sources. Several projections to choose from. So there are the various map projections available from which we have to select our as per our requirement. Projection inevitably distorts at least one property will be distorted, which can choose. We have to choose the basically suitable map projections which can control the errors. Thank you very much. In this lecture, we discussed about basically the datums or the ellipsoid and the two-dimensional basically conversion from three-dimensional to the two-dimensional conversion. That's the map projections. Okay, and various map projections available, various coordinate datums are available. We have to select as per our requirement. Thank you very much.